Alrighty, so we just had the video on the component method for solving these force vector problems. And now what we want to do is look at the other method which engineers generally use, which is called the triangle rule. But before we can do it, we first need to just briefly review two pieces of trigonometry. First is the law of sines. And if you remember from our trig review, we had the law of sines said sine of alpha over A is sine of beta over B. And it's basically given some triangle. Let's say we have a triangle that looks like this. Call this alpha, beta, and gamma. Then this would be side A, side B, and side C. So you could see alpha goes with A, beta goes with B, and gamma goes with C. So the law of sines is basically a relationship between the size of an angle and the length of the side opposite to that angle. And it's fairly clear that the bigger the angle, the longer the side is going to be. Because, of course, for instance, if you look at these two sides here, if that angle widens, then where this is located and where this is located widens as well. So length A gets bigger. The other thing we need to know is the law of cosines. Black. Law of cosines. And what this says is that the length of A squared is B squared plus C squared minus 2 beta gamma cosine of alpha. And so what this is basically, I'm sorry, not beta and gamma, BC cosine of alpha. I apologize. So A squared, the length of side A squared is B squared plus C squared minus 2BC cosine alpha. And it's basically like a generalization of the Pythagorean Theorem. Remember, Pythagorean Theorem and the sines, the SOHCAHTOA stuff, all of that requires the triangle to be a right triangle. However, obviously, not every triangle is a right triangle. In fact, almost all triangles are not right triangles. And so, if we don't have a right triangle, we can't use Pythagorean Theorem and SOHCAHTOA to solve problems. Thankfully, law of sines and law of cosines can work. And if you notice, if alpha, for instance, is 90 degrees, then this third term, the minus 2bc cosine alpha, goes to 0, and you're left with the Pythagorean theorem. So this is like the Pythagorean theorem only for triangles that are not right triangles. And so if you're given a triangle and you need to figure out parts of the triangle that you don't know, if it's not a right triangle, that is, one of the angles is not 90 degrees, then you have to use law of sines and law of cosines to solve it. Okay? In the component method we did last time, and what physicists generally do, they purposely create right triangles so that they could use SOHCAHTOA and Pythagorean theorem and the like. However, sometimes it causes more work than you need to do because you could solve the problem using a regular triangle that's not a right triangle in less steps. But in order to do so, you have to use these equations instead of the right triangle equations. So there's a give or take. SOHCAHTOA is easy, but it takes more steps to do because you have to make right triangles. Law of sines and law of cosines, you don't always remember it very easily, but it's very easy to create a triangle out of. So there's pros and cons. Anyway, given that these are the equations we're going to use to be able to calculate off of our triangle, let's actually see an example of solving a problem using the triangle rule. So we saw last time this example, which was we have a hook, screw type device that's screwed into the ground, and we've got two ropes. The first rope has a tension F1 of 100, and he's located at an angle of 15 degrees. And rope 2 has a tension F2 of 150. Let me redraw this, give us a little more room. So F1, 100, at an angle of 15. F2 is a tension of 150. And he is at an angle with respect to the vertical of 10. And I'm going to ask the same question. Calculate the net force acting on the screw. Last time we did it by components, which meant we took each force, broke each force into x and y components, added all the x components together to get a final result in x, added all the y components together to get a final result in y, then used Pythagorean Theorem to find the magnitude of our resultant vector, and SOHCAHTOA allowed us to find the direction. Now I want to do exactly the same thing, but instead of using components, I'm going to make a general triangle which shows how the forces add together, and then the third line of that triangle will be the resultant vector. So what we want to do is start with one of our forces. So let's say we start with F1. Let's draw it. So here's the beginning, and I'll draw F1. Okay, and what do I know? The angle that F1 makes with respect to the horizontal is 15. Then what I do is I take F2, and I'm going to draw F2, but I'm going to draw it on the tip of arrow F1. And so if you remember when we first discussed vectors and how to add vectors together, back in physics I showed you how to do it graphically, and we did what was called the tip to tail method. So you draw one vector, then on the tip of that vector you draw the second vector, and then what you know is that the line that goes from the origin to that final tip is the resultant. That's basically what we're doing. So F2 now, if you remember, F2 is a line that's 10 degrees with respect to this vertical. So it's going to look like this. Okay. So So this is 10. Then what we have, the red line I'm about to draw, is a line from the origin to this final tip. So there he is. That's my resultant R. So now we have a triangle. Here's our triangle. I'll draw it again over here in gray. One line, another line, and then the resultant. And what I want to find is this resultant here. What do I know? Well, I know this bottom line, that was F1, he's 100. And I know this right side line, that was F2, that's 150. So I know those two lines. And what would be great is if this was a right triangle, I could use Pythagorean Theorem to find R. The problem is I don't know if this is a right triangle. And since I don't know for sure, I have to assume it's not. So since I don't think this is a right triangle, I can't use Pythagorean Theorem. So I'm going to need a little more information. I need to know something about the angles in order to figure out R. So what do we know about these angles? Well, like I said, in our left picture here, I drew the axes, and we know from our drawing that the blue line, F1, makes an angle of 15 degrees with respect to the horizontal. Okay, so let me go ahead and just draw another horizontal right here. That may be useful, I don't know. This process I'm about to show right now is what makes some people like triangle rule and some people hate triangle rule. With the component method in physics, it's straightforward. Every single time you draw a right triangle off of your vector and get the x and y components. With the triangle rule, some of these are very, very straightforward to figure out what the angles are, and in some of them you have to use some creativity. There's not one strict, straightforward way of figuring these angles out. Now, after you've worked and practiced a few problems, you kind of get the hang of it, and you know some of the tricks to employ to try to figure these angles out. But sometimes you may try something and it doesn't help. For instance, I just drew this gray horizontal line. That doesn't really tell me anything, except notice that I have a vertical gray dotted line and I have a horizontal. I know that total thing is 90 degrees. But I don't know, for instance, what this angle is. I have no idea. At least I don't think I do. Let me think. Do I know what this angle is? Actually, I do. Notice this. If this green line is F2, and F2 makes an angle of 10 degrees with respect to the vertical, then it must make an angle of 80 degrees with the horizontal. Because from horizontal to vertical is a total of 90. This top vertical angle is 10, so this must be 80. Okay. I don't know if that helps, but we have something extra. All right, what else can we do? What I want is I want to find these internal angles. I want to find that angle, and this angle. I don't know them yet, but I'm getting pieces of them. Now notice this. Looking at this left side triangle over here. If I redraw it a little bit, one thing I can try is I can try to elongate this line. Okay, it's fake, that's why I'm doing it dotted. If I do that, then what I know is the angle from here to here is 180 because it's a straight line. I also know that if this is my dotted vertical line, this much of it right here is 10, right? F2 makes an angle of 10 degrees with respect to the vertical. So I already know 10 degrees. What else? I also know that this horizontal line, this is 15 right here. So what I can do is this. Notice this blue angle, the blue angle there of 180. What is it made of? Well, first it's made of this angle, call it theta 1. Then it's made of this 10. Then it's made of this theta 2 thing right here. Right? If I add those three pieces, I get 180 degrees. What I want is just the theta 2 and the 10 added together. That'll give me this angle, this green angle here. Right? That's all I want. I only want this amount of it. So the theta 1 I could care less about. But I may need to figure out what theta 1 is to get the rest of it. So, what can we do? Well, remember, at this point, right over here, I said from the horizontal up to the green line must be 80 degrees. Well, notice on this picture I drew right here, I have the horizontal here, up to the green line, which is here. So that says this theta 1 plus the extra 15 must be that 80 degrees. Well, that's good. That'll give me theta 1. So theta 1 must be 80 minus 15, which is 65 degrees. So now I know this theta 1 sitting here is 65. So this now can give me theta 2. Theta 2 must be 180 minus 65 minus 10. So 180 minus 75, that must be 105 degrees. Good. Now I have theta 2. I've got all these angles that make up the 180. What was it I wanted? Remember, I want on this right side triangle over here, this blue angle, this interior angle. Looking at my gray triangle as a picture, that's the 10 degrees plus theta 2. So now I know this angle right here must be the 10 degrees plus theta 2, which I now know is 10 degrees plus 105, which is 115 degrees. Phew, all right, so all of that gave me one of my angles. I now know that angle is 115 degrees. Let's go back over that again just to be sure. I don't know from the starting point how I'm going to figure my angles out. I have to be creative, look at the things I know, and kind of treat it like a puzzle of can I figure out this unknown information given the information from my triangles. So I started with the basic triangle, which is here. Said, I want these interior angles. And then what I started to do was I put those on my left triangle, the horizontal and vertical lines. Because the only information I know from my problem is what is the angle of each of these forces with respect to either the horizontal or the vertical. Then I said, okay, how will that help me? Well, what I had to do was I had to look this F2, my green arrow. I know with respect to the vertical is 10 degrees. and thus with respect to the horizontal must be 80 degrees, because from horizontal to vertical is a total of 90. Next, I drew another triangle down here, just so I don't mess up my original triangles. And I said, what else can I figure out? The other trick I do, other than the horizontal and vertical dotted lines, is I'll try to extend one of the main lines of the triangle. And in this case, I extended my F1 line as the blue dotted line, just extended it out. And then I use the fact that that F1 line is 180 degrees, because it's a straight line. From there I said, okay, given that's 180 degrees, how much of it do I need to find out? Well, remember, I just want the interior angle, so it's this left side piece, which I called theta 2, plus the 10 degrees, which I already knew. So I used this equation here that said 180 degrees, the full straight line angle. What is it composed of? Well, remember, it was composed of theta 1, which was this right side angle over here, plus the 10, plus theta 2. All right. Then I went back up to my left triangle where I had the gray dotted lines. And I said, remember, the vertical to the horizontal is 90 degrees. I already know 10 degrees of it. So the rest of that angle, which for us is theta 1 plus 15, must be equal to 80. And I said, all right, well, solve for theta 1. That gave us 65. Once I knew that 65, calculating theta 2 was straightforward. We got 105 degrees. So with that information, I now have everything I need to know for that interior angle, because what it is theta 2 plus the extra 10. So that's 115. Now what can I do from here? Well, from here, the rest of the way is going to be fairly easy. This was definitely the most challenging part of the problem, getting one of these angles. But once you have one of the angles, the rest seems to flow okay. Now we're going to make use of the law of cosines and the law of sines to try to get the rest of the information. So let me erase some of this just to make some room. Okay. So what do we want to do? Well, notice what we have. We have this side, we have this side, and we have this angle here. What am I looking for? I want this R, and I also want the angle. Well, the angle, of course, if this is my R vector, then the angle I want is the angle with respect to the positive x-axis. So I want this theta. So what is that theta? Well, that main theta is whatever this angle is here, let me call it alpha, plus that extra 15 to the horizontal. So if this is alpha, I'll let this angle here be beta. Then if that's true, then this angle here, I'll call it gamma, just to have labels. Okay, so those are the two things I want. I want R, and I want theta. Well, we have law of sines and law of cosines. Can I use law of sines? Let's look at what law of sines says. Law of sines says, okay, there's 4 pieces of information in this equation. There's 2 angles and there's 2 sides. So I can only have one unknown. So let's say I'm looking for a side. Let's say I'm looking for A. Well, in order to calculate A, then I need B, which is the length of a side, and then I need two different angles. I need A's angle and I need B's angle. Do I have that? Let's say I'm looking for R. If I'm looking for R, then I need one of the sides. Well, I know both of them, so that's fine. Then I also need the angle for R, which I know, that's gamma, I have it. But then I also need the angle for the side I know. But I don't know either of those two angles, alpha or beta. So I can't do that. What about, obviously, I don't have to solve for a side, I could solve for an angle. Maybe I want to solve for alpha. Let's say I want to solve for alpha. If I want to solve for alpha, then I need alpha's side, A, which is this 150, it's the one opposite. Then I also need another side and that side's angle. Well, I do have another side, this 100, but I don't know beta, which is 100's angle. I do know gamma, but I don't know gamma's side length, which is R. So all of this is telling me I don't have enough information to use the law of sines. What about law of cosines? If I want to use law of cosines, what do I need? Well, I'm looking for a side length. I need the other two sides, and I need the angle for the side I'm looking for. So let's see. Let's say I want R. If I want R, I need the other two sides. Well, I know the 100, know the 150. Good. But then I also need to know the angle for R. Do I know that? I do. That's this gamma. I just calculated it. Aha. So I now know what I can do. I can use law of cosines to calculate side length R. So what does the law of cosines say? R squared is the other two, 100 squared plus 150 squared minus 2 times 100 times 150 times the cosine of the angle which is opposite to R, which for us is gamma, 115. And there we go. We have all the information. This is just an equation. So we plug the equation in. Let's see, cosine 115 times 2 times 100 times 150. So all of this is negative 1267.85. All of this stuff on the right. So I have 100 squared plus 150 squared minus negative 1267.85 gives me 33767.85. And then I take the square root, and that gives me 183.76. Oh, I'm sorry, I just noticed a mistake. The mistake was my decimal place is wrong right here. It's not 1267.85, it's 12678.5. Forgive me. Minus 12678.5. So again, it's 100 squared plus 150 squared minus negative 12678.5. Take the square root of that answer, and I get 212.55. There's the magnitude of the resultant. We could go back to our first video where we did this problem using component methods and see that we got a very similar answer if not exactly the same. Depends on how much rounding you have, but we got 212.5. Okay. So that's half the answer. That's the resultant. That's the magnitude of the net force. I still need the direction. How can I get the direction? Well, let's use Law of Sines. Law of Sines, I'll do it over here. Law of Sines says, let's say sine of alpha over alpha's side, which is the side opposite to him, which is 150, is something we know completely. That is, a side length and his angle. Well, I just calculated a side length r, and I know r's angle, which is gamma, so I could use r. Oh, I'm sorry. Sine of gamma over r. So let's plug our numbers in. Sine of alpha equals sine of gamma, so sine of 115 over r, 212.55 times 150. So what does this say? Sine of 115 divided by 212.55 times 150. Then take the inverse sine of that. Tells us alpha must be 39.76. But don't box this yet. Remember, alpha is not the thing we want. What we want is this theta. Right over here, this red theta here. Because what I want is the angle with respect to the horizontal. So how do I get theta? Theta is alpha plus 15. We figured that out earlier. So 39.76 plus 15 gives us 54.76 degrees. And again, if we go back to our component method, we should have gotten something like 54.8. All right, so this is the triangle rule. Now, this was a fairly difficult one. I randomly chose an example problem, and it turned out that the calculating the unknowns on this triangle was a little bit harder than it normally is. Sometimes they're a breeze and you go through them really quickly. Sometimes are like this, where you have to really kind of think outside the box, try a bunch of different things, and work your way to the answers. For this one, we had to do a few things. The big tips I can give you when working on triangles is something like this. Say you have a triangle that looks like this. This is the R you want, let's say. So he will be gamma. Call him alpha and beta. So this is A and this is B. What are the things you can do? One thing you can do is, of course, make your little horizontal or vertical axes. Because a lot of times the question will give you your forces with angles with respect to the horizontal or angles with respect to the vertical. What else can you do? Well, you can try, let's say this was your F1 and this was your F2. You could try extending F1. Just continue drawing the line. And then you'd use the fact that from here to here is 180. Just like you could use the fact that from here to here is 90. Okay? And you do these kinds of tricks, and you say, okay, if I do that, what does this tell me? Well, notice if this whole thing is 180, here's some theta 1 part, here's some theta 2 part. So theta 1 plus theta 2 is 180. But then I also have, we could call this guy right here theta 3, that theta 1 plus theta 3 is 90. And we can keep going with this kind of stuff, thinking our way through it like a puzzle to try to figure out eventually I want the alpha, the beta, and the gamma. I don't always need all of them. Certainly I'm going to need gamma, and I'm going to need R. But sometimes finding alpha and beta help us find gamma. Oh, and don't forget, this is true for all triangles. Alpha plus beta plus gamma, the sum of the interior angles, is always 180. So if I knew two of them, if I knew alpha and beta, then gamma comes for free. I wish there was a better thing I can give you that says every time you do triangle rule, you always do it this way. I can't. Different questions will give you information differently. Some work out so that the triangle is a little easier to see. Some are like this one, where it's complicated and you have to work through it. I promise they're doable. Even the hard ones are. But you may have to sit there and think about it and try different things for 10, 15, 20 minutes until you finally get that piece of the puzzle you need to continue through the process. And always keep in mind that it's the law of sines and the law of cosines you're going to be using. So, one thing to remember is for law of sines, if what you need, for instance, if you want the length of a side, if that's what you want, what do you need? Well, you need his angle, that is the angle opposite to the side you're looking for, and you also need one total set of info. So for this, example triangle written here, if I wanted A, what do I need? I need alpha, and then either B and beta, that is side B and B's angle, or C and gamma. Right? A total set, the side and his angle. Anytime you want to use law of sines, then whatever it is you're looking for, you need the other piece. So if you're looking for the side, you need his angle. If you're looking for the angle, you need his side. But then, on top of that, you also need one whole set, a side with his angle. Okay? For law of cosines, in general, you're going to be using this usually to find a side length if you know the other two sides. However, it's key, it only works if you also know his angle. In order to find A, I needed alpha to do it. If I want to find B, then I need beta to do it, and so on. So I can only imagine this seemed very complicated and a little confusing. You may have to watch through it a few times. Definitely sit down with a sheet of paper and work through it yourself, even if you do it along with me, to see where these dotted lines are coming from, where the extension lines are coming from. You can't just watch me do it and then be confident that when I give you a problem on a blank sheet of paper, you can reproduce it. I don't expect anyone to reproduce it, just by watching it the first time. Do it yourself, work it out with me, and then after you've done it with me, if you can see where everything's coming from, then do it yourself without my working it out. Do it with a blank sheet of paper. See if you could come up with the steps needed to solve for the unknown information. I'm going to be given a bunch of practice problems, and as I said, some are a lot easier, so don't be too worried about this particular problem. This was just to show a technique, a general technique. But you have to practice this big time. There's an infinite number of problems I can ask on a test or a quiz, and the only way to feel comfortable is to have worked 10, 15, 20 different problems out. Once you've worked a few, you get the hang of it pretty quick. And then also, when it does come time for tests and final exams and stuff, generally speaking, I won't mandate which method to use. So if you like component method, don't worry, you'll be able to use component method. But for now, especially if you're looking to go into engineering and of any type, you need to be comfortable with the law of sines and cosines method, because a lot of engineers use this method. So you have to be able to see what they're doing and understand how they're working it out. Anyway, that's it for this. As I said, I will be posting practice problems and solutions, but I will also post further videos with some of these problems worked out. Because I know, just looking at the solutions written out, not always straightforward. So I'll work some of those practice problems out myself, record it, so you can hear my thoughts, how I go about solving it, why I'm doing what I'm doing, and hopefully that'll help make this a little more clear. But for now, work your way through this particular example and see if you can get your way through it. Until next time.